Today we will learn about high frequency response of amplifiers. Initially, we have slide set on the review of low frequency, which we will not cover in the class, but I'm leaving the slide set with you for practice. It includes basic review, then analysis of a common drain amplifier in the low frequency region, and a design example, both of which looks very similar to the common source amplifier with some minor differences. Next, we will move into high frequency analysis and then high frequency models of MOSFETs followed by BJTs. So we'll start with the high frequency analysis. Remember, in last class we had focused on how to calculate the low frequency corner. This class, the goal is to focus on how to calculate the high frequency corner or the upper 3 dB point for an amplifier. Remember, this is also known as the FH or F high point. Again, we go back to our single time constant concept. And in this case, we consider a low pass filter. As shown in this figure, we have a resistance R1, R2, and a capacitance C. And the output voltage is across the capacitor C. So as frequency increases, the impedance of C, that is ZC, decreases, which means we know that V naught should decrease. We should expect a behavior of low pass filter. Let's analyze this circuit. And we can see because there is only one capacitor, it should be a single time constant circuit. The voltage across these two nodes can be found by the admittance ratios, where Y1 represents the admittance of R1 and Y2 represents the combined admittance between these two nodes. And we can write that the transfer function is a ratio of those two, and once simplified, it can be written as T nit over 1 plus j omega divided by omega h, where omega h is 1 over C multiplied by R1 in parallel with R2. So as if looking from this point, whatever the capacitor sees, that is R1 in parallel R2, that is the Thevenin equivalent that the capacitor sees. So 1 over the time constant gives us the high cutoff frequency. So what is the difference compared to the low one? There we had looked at a high pass filter, and here we are looking at a low pass filter. So we will next look into high frequency models for MOSFETs. In MOSFETs, our first question comes, where are the capacitors that affect the high frequency response? Because if you remember from last class, all the visible capacitors or the large capacitors, coupling capacitors and the bypass capacitors, we have looked into, and those typically provide the lower corner frequency. Evidently, if something is providing high corner frequency, it means the capacitance should be small, such that the RC time constant is small, leading to a high frequency. So where are these small capacitances? And turns out they are basically inside the transistor. There is a capacitance from the gate to drain, and we call it CGD. There is a capacitance from gate to source, we call it CGS. Now, if we note those two capacitances exist, how does our model of the MOS transistor change based on the capacitance? Remember, the model of the MOS transistor has basically nothing between gate and source because its impedance was infinity, and then we have a voltage control current source GMVGS followed by the output impedance RO. So this is the low frequency model which does not include the capacitors. Now we have to add two capacitors from the gate node, one to the source and one to the drain. So first the CGS, gate to source capacitance, and then Next, the CGD, or gate to drain capacitance. And this gives us a complete high frequency model of the MOS transistor. And it's valid for both NMOS as well as PMOS. Let's try to understand the value of this CGS and CGD. For that, we need to go back to the earlier portion of the class where we had seen when we are in the linear region, that is below here. Remember, the channel is symmetric, which means whatever capacitance we have from gate to the drain side, so this is gate, this is drain, and this is source, should be very similar. We also know that the capacitance from the gate can be given as epsilon by T, where epsilon is written as Kx epsilon naught. So the gate to source capacitance must be equal to the gate to drain capacitance because of symmetry at this point is half of the intrinsic capacitance. That is WL times Kx epsilon naught by Tx. Tx is this thickness. And the half comes because the capacitance gets divided on both sides. Now what happens in saturation region? In saturation region, remember, first thing happens is pinch off, which means there is not that much charge on this right side. So the charge distribution looks like more charge on left side. Which means the field line starting from this gate node mostly terminates on the source. But they do not all terminate on the source. There is a distributed effect. So effectively there is a integration that needs to be done to find the effective capacitance from the gate to source. And once you do that, you can find that there is a factor 2/3 that effectively 2/3 of the total capacitance can be seen from the source side. There is no charge on the drain side because of the pinch off, or effectively no charge on the drain side. So CGD is almost equal to 0. So note that the gate to source capacitance goes from half whatever is the natural C to 2/3 of that as you go from linear to saturation. That's CGS. But CGD goes from half C to 0. That's a idealistic model, but in reality, the drain and source as well as gate have contacts which are shown by these black pillars. So the total capacitance is not only the capacitance coming from the gate to the channels, but it also there is a capacitance between the gate and drain directly and gate and source directly. Let me draw this one. Which means even in saturation, though there is not much CGD coming from the channel formation, there is some CGD stays even in saturation. This portion of the CGD stays in saturation. So we know that CGD is little bit more than 0 because of the overlap or fringing field. And that's how the name of this capacitance goes. And this capacitance, a high effective capacitance, because if you notice, it is between the gate and drain, between which we see a very high voltage gain with inversion. And as we will see in next part of the lecture, that because of that high inverting gain, this capacitance creates a high capacitive effect, which is called Miller capacitance. Okay, so you have understood where the capacitances in MOSFET that creates high frequency response comes from, and how does the circuit should be modified to accommodate the CGS and the CGD. Now you introduce a important concept in the high frequency response of MOSFETs, which is related to the short circuit current gain. And the goal of this is to find effectively the frequency beyond which the transistor is not good anymore. Okay? So that's why we call it the characterizing the MOSFET. So why that is the case? We know this high frequency response will come from some 1 by RC or 1 by time constant. So the highest frequency response I can get when I make R tends to 0, that implies a short circuit, and that's why we make the output shorted. So you know that the output is shorted. We apply a time varying current at the input and find the time varying current at the output and look at their ratio. This current gain can be used to get a voltage gain. Whenever this current gain becomes below 1, the transistor is not of much use, and we will define that frequency as the unity gain frequency, or UGF. Okay, so let's analyze the circuit. We already know how the circuit looks like with CGS and CGD. The only thing we do here is apply a current source at the input, that is II omega, and short the output like this and try to find I naught omega. Okay. So focusing on a KCL at this node, we can write the current coming in I2, that is through CGD, plus the current coming in over here I naught has to be equal to the current of the voltage dependent current source GMVGS. So you can write I naught plus I2 is GMVGS. Because the output is shorted, the node voltage at this node has to be 0, which means the current I2 can be written as whatever is VGS times minus j omega C GD. Right? So the voltage at this node is VGS. So the voltage across this capacitance has to be VGS minus 0, which is still VGS. And hence the current through it would be positive, actually, j omega CT. So once I write I naught is GMVGS minus I2. So I naught is GMVGS minus I2 from this equation. And then when I replace the value of I2, we get that I naught is GM minus j omega CGD times VGS. Now note, typically CGD is small because I would like to operate the transistor in saturation, where CGD should have been close to 0 or tends or effectively is very small, coming from the overlap capacitances. Should say CGD, which means we can approximate this as I naught is almost equal to GMVGS. That is, the contribution in the I2 is not that much. Now we want to find what VGS is. So I'm interested in this voltage VGS. So that should be the current coming into it, which is II, times the impedance seen looking from this node. Because the drain is at ground, it's basically CGD and CGS is in parallel, so they get added and creates the impedance. So the impedance seen from the gate node is given by 1 over j omega times CGS and CGD in parallel. So CGS plus CGD. And the voltage VGS then is basically II times that. So we can substitute this VGS in the I naught equation, and we'll find I naught over II is Gm over j omega CGS plus CGD. The magnitude of I naught over II can be written as Gm over omega times CGS plus CGD. This is very interesting, as you can see that the current gain is proportional to Gm. So if I burn higher current to get higher DC current to get higher Gm, we will get an effective higher AC current gain. Similarly, it is proportional to inverse of sum over C at the gate, which means if I have small capacitances, then effectively I will have a better high frequency response, which is kind of obvious, but that kind of reflects that technology scaling or Moore's law would give us smaller dimensions and smaller capacitances, helping our current gain, short circuit current gain at high frequencies. This term is called short circuit current gain. Let us try to make sense of that result. So as we have seen that the current gain is given by this formula, Gm over omega CGD plus CGS. Because it's current gain, we call it beta, and it's a function of the frequency, so beta omega. And let's define this term, which is independent of omega, as omega t. And we can write beta omega is basically omega t over omega, where omega t is Gm by CGS plus CGD. Or in other words, omega t is simply Gm over C total seen at the gate. Let us try to plot the short circuit current gain as a function of frequency. On the x-axis again we have log 10 of omega. So when we plot the short circuit current gain in terms of dB scale, we write 20 log 10 of beta omega can basically be written as 20 log 10 of omega t, which is a constant, minus 20 log 10 of omega, which creates a negative slope like this, where the slope of this line is given by 20 dB per decade. And let's try to find the intercept of this curve on the x-axis. So that would be when this term magnitude of beta omega in log scale is 0 dB, or in linear scale is 1, which means omega over omega t is omega t over omega is 1. So omega is equal to omega t. So this frequency omega t is very important because the short circuit current gain becomes equal to 1 at this frequency. So this term omega t can be given, as we have seen, by Gm over the total capacitance, which is defined as 2 pi ft, and ft is a very important figure of merit for a transistor. What is the maximum ft one can get? So again, if I have to increase ft, what I'll try to do is try to increase Gm or try to reduce CGS. Reducing CGS is more like a technology parameter, because there is a minimum size transistor that is will give you the minimum CGS for a given technology. And if we need to reduce it further, we need to go technology scaling, which is Moore's law. And increasing GM comes at the cost of power. But what is the limit to this omega t? And it can be written that Ft max is 1 over 2 pi tt, whereas this transition time is effectively the time a electron kind of takes to transit from the input to the output, can be given by the length of the channel divided by the average velocity, which we have looked in the class before. Okay, so that's the maximum Ft that we can get out of a transistor. Now we can start analyzing a common source amplifier for the high frequency region. We have our original amplifier, and now we have two extra capacitances, CGD and CGS, from the gate to drain and gate to source. This is the gate, this is drain, this is source. But we need to think here how to analyze with these 5 capacitances. It is becoming more complex, whereas we had promised originally that single time constant analysis will be easy. So how do we go about making it a single time constant analysis? For that, let us consider this circuit where we have two capacitances, C1 and C2, where C1 is large and C2 is small. Because C1 is large, we know that C1 will short much before C2 shorts. Right? So that creates two cases. First, when we analyze C1, C2 should be open because C2 is much smaller. So the first case is we analyze C1 with C2 open. And the second case is when we analyze C2, because C1 is much larger than it is already shorted. So then C1 should be shorted in the second case. So note that they are different. That for C1 analysis, C2 is open, C2 analysis, C1 is shorted. And that just comes from which capacitance is large and which capacitance is small. So now let's analyze for C1. When we look at C1 and C2 is open, the resistance, that Thevenin equivalent resistance that C1 sees is simply this loop, so R1 plus R2. So the omega L, or the lower frequency, can be given by 1 over R1 plus R2 to C1. Now let's analyze the second case where we want to look at the circuit with C1 shorted. So C1 is short. This is R1. We have R2, and we are considering it from C2's perspective. So the impedance looking in here is simply R1 in parallel R2. So of course R1 parallel R2 will be much smaller than R1 plus R2. So we can say that omega H will be greater than omega L. So what we noticed here is we have two capacitors in the circuit, but we analyze them one at a time, understanding what the other capacitor states should be, open or short, depending on their relative ratios, large and small. And hence we have taken this two capacitor circuit into single time constant analysis. The difference compared to previous case is that there all of the capacitances were similar valued. So versus here, one of them is much larger compared to the other. That leads us to trying to understand how we apply the single time constant both on the lower end as well as higher end. So on the lower end, what we are looking for is effect of large capacitances, which means all small capacitances, all small capacitances should be open circuited, right? And I'm maybe in the circuit there are multiple large capacitances C1, C2, C3. So when I'm analyzing C1, if I am analyzing C1, C2 and C3 should be short circuited. And this gives us the lower corner frequency omega L. Now for the higher corner frequency omega H, we care about the small capacitances, right? Which means all large capacitances are by that time short circuited because the impedance provided by large capacitance at this high frequency is very small, right? And let's say we have multiple small capacitances C4, C5, C6, and let's say I'm analyzing C5, then C6 and C7, these are small capacitances, should be open circuited. Okay, that is over here. And these are called short circuit, open circuit test that gives us FL and FH from inspection. With that, we are ready to apply that on the common source amplifier. So in this case, we know that CGD and CGS is small, much small compared to the three capacitances CC1, CC2, and CCS, right? So when we are trying to find omega H, what do we have to do? We have to make sure all large capacitances are shorted. That is, these three get shorted. And then your remaining circuit is how it looks like now. We have analyzed this circuit earlier without those two capacitances. Now you can analyze this circuit with these two capacitances as well. With that, we have covered the MOS high frequency corner frequency and how to find it. Next, a brief note about high frequency model for the BJT. Similar to the MOS, we can imagine that there would be a base to collector capacitance. We call it C mu, base to collector. And there is a base to emitter capacitance. We call it C pi, which is basically in parallel to R pi, and that's where the name comes from. So this is base to emitter. And everything else remains similar, both the short circuit, open circuit analysis, as well as small signal analysis with these two additional capacitances. So with that, we have reviewed the low frequency, shown how high frequency analysis should be done, presented a model for MOSFETs with CGS and CGD. So CGS and CGD, and presented a model for BJT with C mu and C pi. As a final piece, we will see the application of the high frequency analysis on common source amplifiers. So high frequency response of a common source amplifier, and the rest, Miller capacitance and high frequency responses of common emitter, common base, and common collector would be left as additional reading for this class, and that would not be part of the final exam. I'll provide the slides on Blackboard, and if you're interested, please go through it for improving your concepts. But that is typically an application of what we have said. So again, remember the capacitors inside the MOSFET create the high frequency response, CGD and CGS, and we can give the omega t as Gm over the C total. The common source amplifier has these two capacitances added to it. So at high frequencies, where these two capacitances will start to matter, we have to short circuit other large capacitances, which means CC1, CC2, and CS should be short circuited. And because we will do AC analysis, we will put the VDDs to ground, which gives us this circuit. Note that CC1, CC2, and CS is shorted, and the VDD is set to ground. Now, we have to analyze the capacitors that are inside the MOSFET. So let's calculate the mid-frequency gain. We have analyzed this circuit multiple times, and we can find that the input is a voltage division between RG and RSig, and at the output we have the load, which is RD parallel RL. And we can find the mid-frequency gain as GM times RL dash, because RG is much greater than RSig. So at the input, almost all of the signal applies. Now, knowing the mid-frequency gain as GM RL dash, let us include the capacitors that are inside the MOSFET. So for the high frequency part of the small signal analysis, we'll start including this capacitor one at a time. First, let's consider CGS and then CGD. Remember that for finding the high frequency corner frequency, we are going to do open circuit tests. So whatever capacitor we analyze, the other should be open circuited. So first let's analyze CGS, and hence CGD should be open circuited at this point. So if we do that, we can try to calculate the time constant corresponding to CGS, that is tau CGS, and that would come from whatever impedance CGS sees across it, which should be R signal in parallel to RG. It's close to R signal, so let's call it R signal dash CGS. So that's the first time constant. Now let's analyze the second time constant related to CGD. And for that, we have to open circuit CGS. The circuit looks like this. For this, we have to do some analysis to find tau GD. We need to find the Thevenin equivalent looking from these 2 points. You can write that we are applying Vx between the 2 terminals where we want to find the Thevenin equivalent. Ix current flows into it, and that Ix also flows in here. So the total current that flows into the load is a sum of GMVGS from this branch, from here, and Ix from there. So Ix plus GMVGS flows through RL dash. Then write that this equation. Also, we can write that Vx, which is this voltage, is basically a sum of the 2 voltages, VGS plus VRL, when it's defined that VRL, this side is positive and this side is negative. So we can do some manipulation and find out that the Thevenin equivalent is given by this formula. R signal dash times 1 plus GMRL dash, so this is the midband gain, plus RL dash. So the 2 open circuit time constants is tau GS is something small times CGS, and tau GD is R signal dash, that is small, but a large quantity, that is the midband gain plus 1 multiplied with CGD plus R dash, RL dash CGD. So this time constant is coming from the output, and this one is from input to output. Also note that you can see effectively that CGD looks like a much bigger capacitance, that is 1 plus midband gain times CGD. This effective multiplication of the capacitance is called the Miller effect, which is the next section. Okay, so let's look into this in little more details. So the Thevenin equivalent can be written as the R signal dash times 1 plus the midband gain plus RL dash. So we can rearrange this and basically put it into the form 1 plus midband gain times CGD. So how to make sense of this result? Let's try to look at this closely and see what it means. We see that CGD sees two components, one from the RL dash, that is the output, and one from R signal, that is at the input. And that makes sense because it's between the input and the output. But how do we make sense of the terms that gets multiplied with it? So let's try to analyze again a single capacitor. And when we analyze this, we know that the time constant would be R1 plus R2 into C. However, in case of CGD, it is between the input gate and drain. So if we think of it that way, then it should have been the time constant due to the input capacitances, input resistances, that is R signal dash, which is given by this, and the time constant due to the output, which is RL dash, given by this. But the total time constant is not a summation of these two, R signal plus RL dash. So note that this is not true. Why is that happening? That would have happened if this transistor was not there. Right? If Q1 was not present, but somehow CGT was present, this would have been true. However, since Q1 is present, then we have to think of it a little bit differently. If we analyze the result, we see that the input time constant gets multiplied by this term 1 plus AV mid. So effectively, we can say that at the input, instead of seeing the CGD, we are seeing a total capacitance, which is CGD times 1 plus AV mid, or CM. So that is, on the input side, the capacitor looks bigger by a factor of 1 plus the mid frequency gain. And that is happening because whenever you have some kind of a amplifier providing a gain, so if I have a signal Vi, I'm going to have minus AVVI across this capacitor. So as if I put a small signal here, I'm going to see a large signal there. So how much total change does the capacitor sees? It sees 1 minus minus of AV times what it would have been if this negative gain was not present. So effectively the capacitor looks like bigger by that factor 1 plus AV. And this is basically called the Miller effect or the Miller capacitance. So in summary, the open circuit time constants can be written as from CGS as CGS times the parallel combination of R signal and RG, and from CGD it is the Miller capacitance times R signal parallel RG plus output resistance times CGD. Okay, so the reason we are doing this analysis is to find this upper corner frequency. And we have seen that both CGS and CGD has effect on to this upper corner frequency. Now for CGD, it is as if the CGD comes as a multiplied version, that is Cm, the Miller capacitance to the input, and where the Miller capacitance is given by CGD times 1 plus midband gain. And only the CGD also comes from input to output, because we know that the tau at the output was RL dash CGD. So whenever we look at a circuit with a gate to drain capacitance with a high negative gain across the two terminals, we use the concept of Miller capacitance to bring a high capacitance given by this value to the input and equal valued capacitance CGD, not the high capacitance, to the output. Now we will use that to calculate the gain bandwidth product of this amplifier. So we have found two time constants, one coming from CGS and the other coming from CGD. Because CM also has CGD. And you can see clearly that this term tau GD should be typically much greater than tau GS, because it has this 1 plus AV term in it. So our out corner frequency should be dominated by the time constant, that is the maximum, which means it will create the lowest frequency at which the gain starts to fall. So we look for tau max, which should be equal to tau GD, because that's much higher, which should almost equal to the first term, because this term is smaller compared to the first term. Then we can simplify and write omega h, that is the corner frequency, is 1 over tau GD, is 1 over R signal dash times 1 plus midband gain times CGD. And this is typically much lower than the short circuit current gain. Or in other words, we can simplify and write that omega h is 1 over R signal dash AV mid CGD. So we can then find the bandwidth, which is omega h minus omega L. We know omega L is much smaller to omega h, so it is almost equal to omega h, which is 1 over R signal AV mid CGD. So now, taking AV mid to here, we can write AV mid times bandwidth is basically 1 over R signal dash CGD. And this term is called the gain bandwidth product. So if I have a low AV mid, like over here, then we will have a high bandwidth. But if the AV mid is increased, then we will have a much lower bandwidth or much lower omega h. So in the two cases, omega h1 is much greater than omega h2. That is because the gain in the case 1 is much lower than the gain in case 2. So that's how we find the gain bandwidth product of amplifiers, and we have seen the example of common source amplifier. We will stop here for the class, and we will leave some additional notes for you which are not included in the final exam to learn as further reading if you're interested.